everyone, and welcome back to Mechanical Engineering Essentials, your go-to channel for practical tutorials and tips in the world of engineering. If you're passionate about simulation, design, and real-world applications in mechanical engineering, you're in the right place. Don't forget to like, subscribe, and hit the bell icon so you never miss an update. In today's video, we'll be diving into modeling periodic flow and heat transfer using ANSYS Fluent. This tutorial will guide you step by step through setting up and solving a periodic heat transfer problem using a pre-generated mesh. But what do we mean by periodic flow and heat transfer? Well, many real-life engineering systems, like steam flow in a boiler or air passing through the coils of an air conditioner, involve repeating patterns of fluid flow and heat exchange. Instead of modeling the entire system, we can simulate just a small section thanks to the repeating geometry. In our case, we'll simulate a tube bank, where water flows through and around a series of pipes. One stream of water flows inside the tubes at one temperature, while another flows across them at a different temperature. Because the setup is symmetrical and periodic, we only need to model a small part of the geometry. We'll define periodic boundary conditions in ANSYS to represent this repeating nature, saving time and computational effort while still getting accurate results for flow and heat transfer. In this tutorial, you'll learn how to do the following using ANSYS Fluent. Create periodic zones to model repeating geometry. Define a specified periodic mass flow rate. Model periodic heat transfer using temperature boundary conditions. Solve the problem using the pressure-based solver. And finally, plot temperature profiles on defined isosurfaces for analysis. We'll be working with a 2D section of a tube bank. The schematic diagram you're seeing right now represents the problem setup. The diagram you're looking at shows a bank of evenly spaced tubes, each with a diameter of 1 centimeter. The tubes are arranged in a staggered pattern across the fluid flow. The centers of the tubes are spaced 2 centimeters apart horizontally and 1 centimeter vertically. The depth of the bank is 1 meter. In this simulation, both fluids, inside and outside the tubes, are water, with different inlet temperatures. The Reynolds number is approximately 100, indicating laminar flow. Instead of modeling the full geometry, we'll simulate just one periodic module, using symmetry and periodic boundary conditions to represent the entire system efficiently. Thanks to the symmetry of the tube bank geometry, we don't need to model the entire system. Instead, we'll simulate just a small portion of it, which significantly reduces the computational cost. The computational domain, shown in the image you're currently viewing, represents a single periodic module of the full geometry. We'll apply the following boundary conditions. A mass flow rate of 0.05 kilograms per second is applied to the inlet boundary of this periodic module. The temperature of the tube wall is set to 400 K. The bulk temperature of the crossflow water is 300 K. All fluid properties used in this simulation are based on standard water properties, as shown in the same image. Before we begin, make sure you have the required files ready. You can download the simulation files from our Telegram channel, the link is provided in the video description below. Once you've downloaded the file named periodic_flow_heat.zip, simply extract it to your working directory. Inside the extracted folder, you'll find the mesh file, tubebank.msh, which we'll use to begin our simulation in ANSYS Fluent 2D version. Alright, now let's begin working in ANSYS Fluent by importing and preparing the mesh. Follow these steps. Go to File, Read, Mesh and select the mesh file called tubebank.msh from the folder you extracted earlier. Once the mesh is loaded, it's important to check its quality. Go to General, Check. Fluent will perform a series of checks and display the results in the console. Make sure the minimum volume reported is a positive number. This confirms that the mesh has no serious quality issues. Now let's scale the mesh, because it was originally created in centimeters, not meters. Go to General, Scale. In the window that opens, choose Centimeters from the mesh was created in dropdown. Then click on Scale to apply the changes. Once done, you can close the Scale Mesh window. Just to be safe, go back to General Check and run the mesh check again to confirm everything looks good. Now that the mesh is ready. Before we move on to boundary conditions, let's take a quick look at the mesh structure. The mesh is a hybrid mesh. Quadrilateral cells are used around the tube walls, where we need better resolution to accurately capture the viscous effects. The rest of the domain is filled with triangular cells, which are simpler and faster to compute. You can also right-click on any node in the mesh window to get information about that zone directly in the Fluent console. This is helpful if you're unsure about which boundary is which, especially when zones are named generically like Wall 9 or Wall 12. Now let's create the periodic boundary condition, which is essential for modeling the repeating nature of the flow. Currently, the inlet, Wall 9, and outlet, Wall 12, are defined as regular wall boundaries. We need to convert them into periodic zones. To do this, we'll use the Text User Interface, TUI, in Fluent. Just press Enter in the console to activate the command prompt. Then, type the command you see on screen. You'll be prompted to enter some options. Here's what to type. What this does. Zone 9, Wall 9, becomes a translational periodic zone. Zone 12, Wall 12, becomes its periodic shadow. Fluent automatically calculates the translation vector based on the geometry. All matching faces are successfully paired, and Zone 12 is removed as it's now linked to Zone 9. This sets up the periodic flow condition, which tells Fluent that what enters through one side reappears on the other side, perfect for modeling repeated flow across the tube bank. Now let's quickly explain what we mean by a periodic zone and a periodic shadow in ANSYS Fluent. In simulations where the geometry and flow pattern repeat, like in a tube bank, we don't need to model the entire domain. Instead, we simulate just one repeating unit, and we tell Fluent that whatever exits one side should re-enter from the opposite side. The periodic zone is the side where the flow enters. The periodic shadow is the side where the flow exits. Fluent uses this pairing to simulate an infinite repetition of the geometry, which saves a lot of computational time while still giving accurate results. In our case, we entered the number 9, which corresponds to the inlet wall, named Wall 9, this becomes the periodic zone. Then we entered 12, which is the outlet wall, named Wall 12, this becomes the periodic shadow of Zone 9. So from now on, Fluent knows that anything leaving Wall 12 should re-enter through Wall 9, just like in a real periodic physical system. Now that the mesh and periodic boundaries are ready, let's move on to enabling heat transfer and selecting the right material properties. Enable heat transfer. Go to Models, Energy, Edit. In the dialog box that opens, check the box to enable energy equation. This allows Fluent to simulate temperature distribution and heat transfer throughout the domain. Keycap 3, click OK to close the dialog. Fluent comes with a built-in database of materials, and in our case, we'll use water, liquid, as the fluid, which is suitable for this heat transfer problem. Here's how to add it. Go to Materials, Fluid, Create/Edit. In the dialog box that opens, click Fluent Database. A new window will pop up. Scroll through the list and select Water Liquid, H2OL. Once selected, you'll see the default thermal and physical properties of water appear in the panel. Click Copy to add it to your local list, then close the Fluent Database dialog. Back in the main Materials window, click Change/Create to confirm and apply water as your working fluid. And that's it. Now we're ready to assign boundary conditions with water as the fluid, and with energy equations enabled to simulate heat transfer. And that brings us to the end of this tutorial. We hope you enjoyed the session and found it useful for your ANSYS learning journey. Let's quickly review what we covered. We imported and scaled a 2D mesh of a tube bank. We checked the mesh quality and understood the hybrid structure of quadrilateral and triangular cells. We created periodic zones using the text user interface in Fluent. We enabled heat transfer by activating the energy equation. And finally, we added water as the working fluid using Fluent's built-in materials database. If you found this tutorial helpful, please don't forget to like, subscribe, and click the bell icon to stay updated with all our future videos. Thanks for watching, and we'll see you in the next episode right here on Mechanical Engineering Essentials. Take care and goodbye.